Hello everyone, welcome to this video tutorial. This is the second video tutorial on ANSYS Simplorer software. Yes, in the previous video we simulated the three-phase rectifier circuit, and in this video we are going to simulate the hysteresis current controlled DC motor startup. So in this simulation, just we are going to replace the resistive and inductive load of the previous simulation with a DC motor. And as you know, we can control the current of the armature of the DC motor by chopping of the armature voltage. Yes. So here we use a transistor and a freewheeling diode to control the level of the armature voltage and consequently to control or to limit the armature current during the startup. So as you know, if we apply the rated voltage to the armature of the DC motor when we don't have a back EMF, so the inrush current will be very high and can damage the armature winding. So using this controller, we are going to limit the value of the armature current during the startup. So how we can do this simulation in the ANSYS Simplorer software? We have two methods. In this video, we will discuss the first one, that is using a hysteresis block. And in the next video, we will do the same simulation using the status block. So these are elements that we need to add: a DC motor, transistor, freewheeling diode, hysteresis block, and the equation block to initialize the value of some variables that we need. So here you can see the characteristics of the motor. So let's start. First, we should select the motor model. I copy the previous design and paste it under the project Simplorer 2. So let me delete, yes, the load resistance and load inductor, and from here basic elements, the circuit, electric machines, DC machines. We have several models here, and we should select the DC machine excited with permanent magnet. Yes, you know, we have various type of electric machines separately excited. We can have two windings, armature winding, field winding, or instead of the field winding, we can use permanent magnets. And here we have lumped parameter models of different electric machines. Also, we can do co-simulations and use the finite element model. Yes. So anyway, here I select the DC permanent magnet excitation machine, a DC machine that is excited by permanent magnets. So yes, let's rotate the motor, and this is the dot terminal where the current goes inside the motor. And let's set its parameters. This is the armature resistance, 1.2 ohm. Double click on this, and the armature resistance 1.2 the armature inductance 9.5 millihenry. The value of Ke, rotor flux, is equal to 0.544 Weber. So 0.544 Weber. What is the value of moment of inertia? 0.004 kgm2. The value of the rotor moment of inertia. So, okay, you can make these numbers visible. Yes, here we have only the tag, that is the name of the motor, DC motor. Let me change the name. The name of the DC motor, DCM, and how we can make these parameters visible here. So from output display, for example, this is armature resistance, visibility, the name and value, or both, evaluated both, right? So if I select this one, you can see the RA, and also you can display these names. Yes, to check if you are setting these numbers correct. Anyway, here also we have the load torque. Now this is 0. Yes, actually we are doing the no load simulation. So how we can initialize the value of the load torque and how we can change the value of load torque? I can change the value here manually, or if I want to define a variable and change the value of load during the simulations, I can use the formula block. This is good, and later when we want to do the torque control, we need to have access to the value of the motor torque to be able to define the status of the switch and so on. So the method that is explained in the getting started guide is this. First, we should define an ICA component, the formula block, and define the load variable in it. Also, we can initialize it equal to 0. So here in the search box component libraries, we can write fml init and place this block here. So here we can define the variable, define the equation by clicking on this icon. So I define this variable load equal to, I don't write equal, yes, colon equal to 0. So we define this equation, show this equation, yes. To see this equation here, we define this equation, the value of load is 0, and now I can use that variable here, load. The name of variable could be different, right? But I considered here the same name, but this name could be different. So now let's add a transistor and a freewheeling diode. So semiconductor BJT transistor, let's rotate it. and place the transistor here. And we should change the name of the chopper transistor to TR1 or any name that you want. So here I write TR1 and the type, the model is equivalent line or exponential function. You can change the model. We discussed the model in the previous video. So we select the exponential function type. So okay, and let's do this connection, and also I copy this diode and paste it here to add this freewheeling diode. Yes, when this transistor is off and we have current in the armature winding, this current should continue flowing through this diode. Otherwise, we have sparks and high voltage sparks on armature of the DC motor. So now we should turn on and turn off this transistor, this switch, based on the value of the armature current. Yes, here we have the load and armature current, these two variables. The IA, let's show it, we can make it visible, its name, and also visible the load name, visible its name. We have these two variables, IA and load. So based on the value of the armature current, we are going to turn on and turn off this switch. So in the first case, the simulation that we are going to do in this video, we are going to use the hysteresis block. This is the first method, and also we can control the status of the transistor using the status blocks. So here we should add the 2-point element, the hysteresis block. In the search, you can search TPH. So let's add the hysteresis block here, and let's look at the properties. We have these parameters here. These are the properties of the hysteresis block. Threshold T1, threshold T2, the value 1, value 2, the status of switch that is on or off, and also we should set the initial value that is on. Yes, to start the motor. And here I set the T1 equal to 17.5 amps, T2 equal to 22.5, the value 1, the 2 is 0, initial value is 1, that is actually on to be able to run the motor. And what is the sample time, TS? The sample time, we can consider a number, yes, and the block, according to this sample time, decides to change the output value of the hysteresis block. When we set the TS equal to 0, the sample time is the system time. Yes. And the system sample time is used. So by default, we set it equal to 0. Okay. So what is the input of the hysteresis block? Here you can see the input signal. And based on the input signal that we have its pin here, this hysteresis block decides to be turned on or turned off, right? To set the output of the hysteresis block. We can set the input of the hysteresis block using direct connection of wires, or we can use the variable names. Yes, here I can show the output pin for the armature current IA, show pin, yes, and connect the value of IA to this pin. Yes, so based on the value of armature current, we set the status of the hysteresis block, and then we do this connection to set the status of the transistor. So yes, now we can run the simulation and plot the value of the armature current and the rotor speed. So let's run the simulation. Analyze. Here is the input voltage, the voltage of the capacitor, and here we have the current, armature current, DC motor IA, yes, and also we have the speed of the motor, angular speed, and what is the maximum value of speed? 2800. Yes, this is the maximum speed that we have. And this is the value of the armature current of the DC machine. According to these settings that we have for the end time, the minimum time step, the maximum time step. And as you can see here, we have this limitation on the value of input current. Yes. If I limit the maximum time step size, for example, limit it to 0.1 millisecond and repeat the simulation. So I want to check the curve that we have here. Yes, you can see the switchings, and in this case, as you can see, we are above the maximum value or lower than the minimum value. Yes, the maximum value of the hysteresis is 22.5, but the value of current is higher in these locations because of the time step size and the modeling type. Later, you can see this result. Later, you will see when we set the status of the switch using the status blocks, the simulation is more precise, even with the same time step sizes. Yes, you can see this result for the armature current. We will discuss this in the next video. So, anyway, we added the control block and we got a feedback from the armature current the value of the load is 0, the no load simulation, and we set the status of this switch. How I can define variables and don't draw these extra wires that we have in this model. If I click on this block and show this equation, you can see list of variables. Yes, we have these variables actually according to the elements that we added in software, for example, E1I or diode current and so on. So here we have DC motor. Its name is DCM. Its current is IA. So here I can hide the input pin and also the output pin. The input current is DCM IA. We can use this variable. And the output is actually the name of the hysteresis block. So let me delete these connections. And for the value of current, show pin, no. Simply, we know that this hysteresis block is for controlling this switch. So here, the value of the control signal, use pin, no. What is its status? Is equal to actually the name of this TPH1 dot val. Yes, you can see this variable here. I can show you the variable, the value here. Or actually, I can write dot val. Okay. So, yes, I didn't draw the extra connections that we have for this model. We set the input signal, output signal is for this switch. Let's redo the simulation. Here you can see the value of speed and the value of the current. So now let's extend the simulation time and calculate the no load speed of the motor. Yes, we know that based on the back EMF that we have here and based on the input voltage, the rotor speed will settle on a specific value. So if I let's consider 1 second for simulation here, analyze and plot the rotor speed. This is the no load speed, right? It goes to 10,000 RPM. Here the unit is RPM. Okay, the no load speed of the motor, and this is the armature current. For the no load simulation at the steady state operation, the value of the armature current is 0. And here we limited the value of current using the hysteresis block. Anyway, you can redo this simulation and let's simulate the second case in the next video. Yes, controlling the status of this switch using the status blocks, not the hysteresis band. Thanks for watching.